Okay, so in this lesson, we're going to talk about how energy is conserved. So we're going to talk about the conservation of energy, which we use the abbreviation COE for. Okay, so we have this law of conservation of energy that says, just like every law of conservation of, that as long as we're in a closed system, we don't allow any of the energy to release from the system we're studying, that the total amount of energy is going to remain constant, meaning we cannot create or destroy energy. The energy can change forms, but the total amount is always going to be constant. Okay, so here's kind of the guideline for our problems. If we pretend that all we have is kinetic and gravitational potential energy present, so we're ignoring the other forms for right now, then total energy should be the total amount of kinetic plus the total amount of potential. Okay, well, tacking on to that, well, what if, we have some type of a change in the situation? So the kinetic energy and the potential energy before added together should equal the kinetic energy and the potential energy after. And so this is the way that it is presented to you on your star chart. We will have examples where you might have just two of these on each side, meaning you turn kinetic energy purely into potential energy afterwards, or potential energy purely into kinetic. We will have some examples where you have three. So maybe you have kinetic and potential on the before, but you only have kinetic on the after. Very rarely will we give you a problem where you have all four, just because the algebra becomes more involved and we kind of let pre-AP deal with that. But so the biggest thing for these problems is you need to identify what types of energy do you have before in the system and what types of energy do you have after. Okay, so let's look at a sample problem. We have Tarzan, and he's standing on a 20-meter high cliff, and he swings on a vine to the jungle floor below. How fast is Tarzan swinging when he reaches the jungle floor? So I haven't said anything about velocity yet, so let's see how we're supposed to break down this problem. This is what my relationship would be. This is my COE statement. My potential energy before is equal to my kinetic energy after. Let's understand why. If you think about before, Tarzan is standing. He's standing still on a cliff. If he is not moving, then he does not have any initial kinetic energy. His velocity is 0 to begin with. But he is some distance off of the ground, which is why we have a potential energy on the left side of my relationship. Okay, then he swings, and let's look at what happens at the end. Well, he reaches the jungle floor. Well, now that he's going to be on the jungle floor, he no longer has a height. So we don't have a potential energy after. He does have a kinetic energy because we are interested in the last speed recorded before he hits the floor, like the instant before he hits. So he does have a kinetic energy. That's why we have PE equals KE. That is the physics. That is the hardest part, is to come to this statement. The rest is breaking down our equations and using our algebra. Okay, so if I have mass times gravity times height for my potential energy is my equation. 1/2 mv squared is my equation for kinetic energy. Now notice, because we're talking about Tarzan the whole time, the mass can cancel out. Again, you may leave it in and work the problem, or you may cancel it out and work the problem. It does not matter. But you will notice in this problem, we didn't tell you his mass. So you need to understand that whenever you're not given the mass, it's because you don't need it. Okay, so if we plug our numbers in, we get 9.8 times 20 as my height equals 1/2 v squared. And solving very carefully, I get v equals 19.8 meters per second. Let's look at another one. Here's Tarzan again, running away from a gazelle. Okay, he is running on the jungle floor at 10 meters per second. So if he's on the floor, I'm already thinking he doesn't have any potential energy to start with, but he sure does have kinetic energy because he's going at 10 meters per second. And then he swings up to the top of a cliff, and that cliff is 10 meters tall. So it does have a potential energy, but he's going to be done swinging when he gets to the top. So we have kinetic energy equals potential energy. Set up our equations. Notice that mass cancels. And then be careful. We do not want to put 10 meters into this problem. We want to solve for height and then evaluate if he went high enough. So if we solve for height, he's only going to make it 5.1 meters. So therefore, he's not going to make it all the way up before that rabid gazelle gets to him. All right, so make sure you